So today we are going to start the next topic, Fourier transformation, and this is the last topic for your syllabus. You can see Fourier transformation, how it is defined, students. Yes, this is the transformation. You can see it is from infinite series. So we are going to fully apply the infinite series here and calculate the value one by one. Now you can see the finite Fourier transformation or Fourier transformation of real valued function f of x defined over the interval minus infinity to infinity is denoted by f of s. Okay, and is given by, you can see here, f of s is equal to integration minus infinity to infinity e raised to Isx f of x dx provided the integral exists. Sorry. Okay. Then for inverse Fourier transformation of f of x is denoted by f inverse f of s is equal to, which is nothing but f of x. Then f of x is equal to 1 upon 2 pi integration minus infinity to infinity e raised to minus Isx f of s ds. So please remember this definition, students. So what it's saying, yes, whatever the infinite Fourier transformation we are going to do by taking the real valued functions, it is always defined in the interval minus infinity to infinity. So you can see this is integration from minus infinity to infinity. And then this e raised to Isx f of x dx provided the integral exists. So for infinite Fourier transformation, you have to remember this first formula and exactly its inverse. Yes, students, exactly its inverse is given. F of x is equal to 1 upon 2 pi integration minus infinity to infinity e raised to minus Isx f of s ds. So you can see these are the two important definitions in the Fourier transformation. Okay, next we will just go to the some of the simple applications. You can see applications in the Fourier domain image. Each point represents a particular frequency. Definitely. So you can see here each point in this will represent some domain image, a particular frequency contained in the spatial domain image. So this we are going to represent in this form. So you can see the Fourier transformation is used in a wide range of applications such as image analysis, image filtering, image reconstruction, and image compression. You can see the row in the graph of the unit pulse function. This is a unit pulse function, students. We can take this as, yes, we can take this as f of t. Okay, and its transformation, it is going to transform this to this. We are going to take this as f of omega, that is the function of frequency omega. Translation in the time domain is interrupted as the complex phase shifts in the frequency domain. In the second row is shown g of x. So this is going to become g of t, a delayed unit pulse beside the real and imaginary part of the Fourier transform. So Fourier transform decomposes the functions into eigenfunctions for the group of translation. So this is what we can see. Yes, this is how we are going to get the impulses. Is it clear, students? So apart from this, yes, apart from this, we have again one simple. I've just made. Yes, yes, you can see this, friends. Here you can see in the first frame of the animation, a frequency f is resolved into Fourier series, a linear combination of sine and cosine in blue. So you can see in this image, you can see there is a blue line. They are nothing but sine and cosine series. So the components frequencies of this sine and cosine spreads across the frequency spectrum. So like this, you can see the spectrum it is actually. So you can see, we can see easily the frequency spectrum are represented as the peaks in the frequency domain. Actually, direct delta function shown in the last frame of the animation. The frequency domain representation of the function f is the collection of these peaks at the frequencies that appears in this resolution of the function. A visualization of the relationship between the time domain and the frequency domain of the function based on its Fourier transformation. So therefore you can see here students, the Fourier transformation takes an input function f, that is in red you can see, in the time domain, okay, and converts into a new function, that is in blue you can see f is a function. In blue you can see here students in the frequency domain. In other words, the original function can be though as of being amplitude given time, and the Fourier transformation of the function is amplitude given frequency shown here. A six component approximation of the square wave is decomposed exactly for simplification into six sine waves. This component frequency shows as very sharp peaks in the frequency domain of the function as shown in the blue graph. So this is what just I have made a simple animation I have just collected for understand how this we are going to take the sine function, cosine function of the Fourier transformation. So this is how we have the sine function and cosine function students, and one by one we are going to study this using the example. So now we'll just take one example students. Is it clear? So we'll take one example. Write down example 1. Okay. Example. Yes. So quite easy example we have here students. So please write down the example. Find Fourier transformation of f of x is equal to 1 0 for mod x is less than 1 and mod x is greater than 1. Also, hence evaluate integration 0 to infinity, it is sine x upon x dx. So we are going to solve this example students. So before this you should also know some of the properties. So just take down some properties here. So to simplify the example, you should know very simple properties. I think you have come across these properties. Even in the first lecture of the Fourier series, I have given these properties, and also I have given quoted some applications of Fourier transformation in the Fourier series also students. So this is a continuation of Fourier series actually, and Fourier series what it is restricted towards some of the fixed intervals, but here you can see it is not restricted, it is continuous. Yes, it is ranging continuous from plus infinity to minus infinity or minus infinity to plus infinity. So we'll just take some of the properties. First one is the linearity property. Okay, just I will show you how this is linearity. So it must satisfy this condition, that is f of a f of x plus b g of x is equal to, it is a f of s plus b g of s. So they are just quotation students. Please remember here a and b are constants. Okay. Then we have change of scale property. So this is quite useful to solve the examples. Change of scale property, if it is required, we are going to take this. Suppose a function is given f of ax, which is equal to, we can write this as 1 upon a f of s divided by a, where a is not equal to 0. This will be understandable when you solve the example, students. Okay, and then I will show you how we use this one by one. Next one is also very very important, that is shifting property. So what it says, if the function is given in the form of f of x minus a, so we can write this as e raised to I s a f of s. Is it clear? So next one is again fourth one, it is modulation property. So we use this property also, that is a function is given here, that is f of x cos ax, which is equal to 1 upon 2. We can write the same as f of s plus a plus f of s minus a, students. Okay, so this is how we are going to use this properties. I will just read out once again. First one is the linearity property, means any value is multiplied to the function, we can take outside the function. Suppose 2 is there, 3 is there, you can see where a and b are constant. So constant terms we are going to take outside the function. Okay. Next, change of scale property means if you take 1 upon a, then we can also divide in this function, that is s divided by a. Shifting property, what it says, f of, this is Fourier series f of the function. This is small f is the function runs. This capital F is the Fourier transformation. So this is all transformation takes place. So f of x minus a is given. We can write this as e raised to I s a f of s. So again, next one is a very simple modulation property. You can see the Fourier transformation f transform function f of s cos ax is equal to 1 upon 2 f of s plus a plus f of s minus a. So this property we are going to use to solve the example also, students. So this is what the example they have given here. A very simple example it is, but remember, definitely here we are going to use integration. Yes. So we'll just see. So what they have given here, students? Yes, the function they have given. So how you will simplify, I will show you. See, so first I will take down what all the things given here. So here they have given Fourier transformation is given. So I will just take here Fourier transformation. Okay, we are going to transform. I think some of the students have watched transform film. I should not say, but generally you have seen the transformers, right? One, two, so many are there. So many of the students have watched that film. The same things we are going to do here. Fourier was a scientist. What he did, he transformed these functions into various. So now I can see, using the Fourier transformation by given the function like this, we can going to transform in this sin x upon x. So this is what the transformation of the functions we can see as friends very easily. So now first you are going to write the formula of Fourier transformation of f of x is given by, that is f of x is equal to integration minus infinity to infinity e raised to I s x f of x dx. So first you have to write the Fourier transformation. Is it clear, students? Now I can see how this has been given. Okay, so just graphically I will show you. Whenever there is given mod x. Yes, mod x means what, students? Yes, suppose if you take in between 0, the value will be in terms of negative, also in terms of positive equally. Yes, very very important, equally. So therefore this is less than 1. Less than 1 means this will indicate -1 to +1. This range, x range is from -1 to +1. So this is what the function says. This is our limit, or the interval we can take, -1 to +1. So it is always 1. Please remember. Okay, students. Similarly, greater than 1. Greater than 1 means what? Mod of x. Yes, greater than 1. That implies this will be like this. -1 is also greater and x is also greater. So means whatever the function beyond +1, this value, and more than -1, this 2 will give you this function, and this will tend to 0. Is it clear? So more than +1, less than -1, this side, LHS and RHS. Okay, so whatever the value, whatever the function is there, it is always 0, and between -1 to +1 it is always 1. So this is graphically I have shown you how this represents. Okay, so we'll just take now this function again. Now substitute. First you break this integration, because minus infinity to infinity is that this is minus infinity to infinity, suppose, but we want only the function must be -1 to +1. Is it clear, students? I want this function f of x is equal to 1 when it is mod x is less than 1. So I require only this much. I don't want this part and this part, so I will delete it. So to delete this value, what I will do, I will break this minus infinity. How? Minus infinity to 1, I will take this part. Okay, then next I will take this part and I will take this part. So this is from minus infinity to -1, which is 0. This is -1 to, sorry, this is -1 to +1. This is function is 1, and this is +1 to plus infinity. This is function is also 0. So I will integrate this integration. I will break this into, so one by one you can see here, minus infinity to infinity e raised to isx f of x. Sorry, again I have taken same. I have to break this integration, students, from minus infinity to, I will take here -1. Is it clear? So this will be e raised to minus isx f of x dx plus. Now what will be this continue? -1 will continue here, and I will put here +1 e raised to isx f of x dx plus. So I will again continue this part. Yes, this I will continue here. So this is again +1 to infinity e raised to isx f of x dx. Is it clear, students? So like this, I have break this integral in this 3 parts, because I want this -1 to +1. The function is 1. F of x is 1. But whereas this is 0, this is 0. Therefore, I will cancel this and make this 0. I will cancel this and I will make this 0. So only what is remaining here, students? Integration -1 to +1 e raised to isx dx. Tell me why I have taken this function. Function is f of x is equal to 1 in the interval -1 to 1. Therefore, I have taken this in this form. So now, after simplification, now we are going to apply the integration. Very, very clearly understand, student, this, that whenever the Fourier transformation given in this form, first you have to go through the interval. Don't apply the integration directly. Then after splitting the values properly in the form of the interval, then you will substitute the function. Then you are going to go for the integration. Now I am going to substitute the integration, students. Now I can see I am going to take this integration. Yes, I think you remember integration of e raised to ax. So I have done a lot of integration on this ax. dx is given. What is the integration? E raised to ax upon a. That is whatever the constant terms are there, that I am going to take down. Okay, that is coefficient of x. Now, what will be the integration of e raised to I s x? Yes, friends, coefficient of x, I and yes, I will take divided by I into yes below. Then our lower limit and upper limit you can take plus 1 to minus 1. Fine. Now I will simplify this. This is equal to, you can see here from first I will take 1. X is equal to 1 and x is equal to yes minus 1. So I will first substitute and I will take out I yes is constant, so I will take is outside. Am I right? So now I will substitute e raised to is, that is I have substituted x is equal to 1 minus e raised to minus I yes. So this is what we get the Fourier transformation. Now what it says, please remember this, some of the formulas we know that you can directly practice this examples. It is sin x is equal to e raised to ix minus e raised to minus ix upon 2i. Similarly, here you can see, similarly I want e raised to is minus e raised to minus is. I can write like this, 2i I will take this side, so this will become 2i, but please remember here instead of x we are going to take yes, therefore this will become sin yes. Is it clear? So here x is there, no problem, I have taken here yes. So this value will become now like this is equal to 1 upon I yes, substitute the values, that is 2i sin yes. So I have taken like this. So here you can see I will get cancelled, so this will be equal to 2 sin yes upon yes. Is it clear? So this is just Fourier transformation. So this is, we have Fourier transformation. Please remember we are going to go for inverse Fourier transformation, because we are going to evaluate integration 0 to infinity sine x upon x dx. Okay, so this is Fourier transformation, but to deduce the next equation I have to use inverse Fourier transformation, students. Okay, so what is the Fourier transformation formula? Yes, please remember, as already given. So f of x is equal to 1 upon 2 pi integration from minus infinity to infinity f of yes e raised to isx dx. Please remember this, students. Okay, so this is minus. Okay, so now this, whatever the function we have taken f of x is nothing but f of s. So means this value is our f of s. This is in terms of s, students. So therefore this is f of s. So now please take this value and substitute it in the inverse Fourier transformation. You will definitely get the answer. So now I will substitute this value. So this is equal to 1 upon 2 pi. Okay, integration minus infinity to infinity. This value I am going to substitute. It is 2 sine yes upon yes, and I will keep this e raised to minus isx yes dx. Okay, now you can see here, students.
Sir.
Yes, please tell me, beta.
Sir, into ds.
Into ds. Oh, correct. Yes, because we have taken the function f of yes. Yes, very good. So it is ds, because this function we have taken f of s. So when its function is representing s means integration d yes it must be. Very good, thank you. So this will be equal to, now you can see this 2 and 2 will get cancelled. Is it clear? Okay, so this equation will become now 1 upon pi integration minus infinity to infinity. This will become sine s upon s e raised to minus sine sx ds. Now you can see here students, I'm going to put the value, put x is equal to 0, so that this function I may get like this. That implies I'm going to restrict this function for f of 0 because yes, we'll come to this. Yes, so I want, why I'm substituting f of x. This is the common question for all the students. But please remember, in this function that is minus 1 to plus 1, f of 0 is 1. So from graph we can see y f of 0 I am going to take because this is equal to 1. So therefore x I am going to choose 0. So this is what the trick you have to understand, because minus 1 to 1 definitely 0 will come. So when I take x is equal to 0, you can see f of 0 is equal to 1. So like this I am going to deduce this. So now that implies this function, I will continue this equation students. So this will become 1 is equal to 1 upon pi, okay, integration minus infinity to infinity. This is going to become sine s upon s, and this e raised to minus I s x. So x is 0, 0 into s I is 0, e raised to 0 is 1. So therefore this is 1 and this is ds. I think you remember the property when the function is from minus infinity to infinity, minus infinity to infinity, f of x dx is given. You can write this as 2 times 0 to infinity f of x dx. So this property you have to remember students. Please remember, I think in the Fourier transformation, Fourier series also we have used this. So this is equal to, I will bring this pi on this side. So 1 into pi will become pi is equal to, this is 2 times integration 0 to infinity sine s upon s ds. Okay, now I will bring this 2 below, so that implies this will become pi upon 2 is equal to 0 to infinity sine s upon s ds. Now you can see here students, yes it is in terms of s, no problem. So yes can be taken as some variable, so I can also choose as x. So therefore integration 0 to infinity sine x upon x dx. So wherever s is there, I've just chosen some other variable x, which is equal to pi by 2. So this is what we get the answer. So that is integration 0 to infinity sine x divided by x dx. We have calculated, that is pi upon 2. Is it clear students? If we have any doubt, please ask me. Yes students, if we have any doubt, please ask me students.